An example of a compound inequality is one that looks like that. Similar to what we did on Friday, except there's 3 parts to it. A middle and 2 sides, and 2 inequality sides. This is an example of an AND inequality. The 3x minus 4 has to be less than 11, and it has to be greater than or equal to 8. 2 things going on at the same time. So 2 different things have to be true for the x mystery number to work. If you put in a number for x and 3x minus 4 is less than 11, that's great. But when you put that number in for x, it also has to be greater than or equal to 8. That's an example of an AND problem. There are also OR problems, and those are problems where only one of the 2 has to be met. Those are a lot less restrictive, where, for example, 3x minus 4 is less than 11, or 3x minus 4 is greater than or equal to 8. That's different. When you have a compound inequality like the one on the screen, where you have 3 different things going on at the same time, those are always AND problems in here. Okay? So, if we're going to solve this, we're going to need to get that x by itself, so we're going to add 4. All right? If you're going to add 4 there, you're also going to add 4 with the 11 and the 8. So for the 3 sections of the inequality, you're going to add the 4 to all 3 sections. Kind of fun. When you do that, you get 12 is less than or equal to 3x, which is less than 15. Then, to get the x by itself, you would divide by 3, and again, all sections must be divided by 3. So you end up with that. Sir?
I thought that when we multiplied and divided, like we had to switch the signs.
That is a very good question. What did he say that was wrong? Emma?
It's when you multiply or divide by a negative.
Well, it has to be multiplied or divided by a negative. Good participation there, Log. Very good. And good retort there, Emma. And good job, everybody else, for raising your hand. All right, so let's say I'm going to graph this. I'm going to graph x is less than 5. And that would look like that. I'm going to graph x is greater than or equal to 4. And that would look like that. But remember, both have to be true. So if I have x is less than 5 as a red graph, and x is greater than or equal to 4 as a blue graph, the area that's both is the area that's purple, that's red and blue at the same time. And that's the area in the middle. Okay? So, these arrows that I drew really aren't there. I was just drawing those to show you really how it ends up working. It's the overlap of those 2 graphs. All right. The numbers between 4 and 5, including 4, but not including 5, when you put them into the inequality, are true. Anything else is false. So your picture, my picture up there, the purple numbers are the numbers that are true in our inequality. Okay? I call that type of graph a skateboard graph. And that's the type of graph you're mostly going to find in an AND problem. When you have an OR problem, I call those graphs pigtail graphs. Because what you're going to have there most of the time is arrows kind of squirting out. Okay, that's just what I call them. You can call them whatever you want. Skateboard and pigtail. If I'm going to do an OR inequality, there's no triple to it. You're just going to have two different inequalities with the word OR written between them. Okay? And you very simply solve two different inequalities like we did Friday, and you graph them separately on the same number line. So for x plus 3 is less than 2, we're going to subtract 3 and get x is less than negative 1. And on the right side, we're going to divide both sides by negative 1. And McCabe, tell me something else.
X would be greater or equal to 4.
Has to be greater than or equal to 4, because when you divide by a negative, we flip the inequality. Good job.
Okay.
All right, so now we have our two solutions, and we just graph those separately on a number line, and it should look like one of my ponytail graphs. X is less than negative 1. X is greater than or equal to 4. There you go. Pigtail, not ponytail. Doesn't look like a ponytail at all. Unless you don't know how to do hair.
True.
Questions? All right. Now let's do an absolute value inequality. All right. First thing we have to do is determine whether or not the absolute value inequality is going to be an AND problem, which would be a skateboard graph, or an OR problem, which would be a pigtail graph. And the clue for you is painted on the wall. Land and Gore over Natalie's head over there. If the problem is a less than problem with the absolute value on the left, it is an AND problem. Land. Less than and. If the problem is greater than, it is an OR problem. Gore. A less than problem, unless it's some sort of no solution or all solutions or whatever, a less than problem is going to yield a skateboard graph, and a greater than problem is going to yield a pigtail graph. That's all that. That stuff went up there a little prematurely. Sorry about that. So, here's what I do. I am going to break up my absolute value like we did last Thursday when we were doing absolute value equations. So we're going to break up the absolute value into x is less than or equal to 5. And then we break it up into another part to x is greater than or equal to negative 5. Notice that we flipped the inequality sign and we inverted the sign of the number as well. Both of those switch. So we have x is less than or equal to 5, and we have x is greater than or equal to negative 5. Is this an and problem or an or problem? Does anybody know? Why?
It's less than.
It's an and problem because it is less than, which means that when we graph this, these graphs should overlap, yielding us some sort of skateboard-looking graph. And so since we only have one variable in the absolute value, we don't even have to solve anything. We're done. So when we graph these, there is our graph. Less than or equal to 5, greater than or equal to negative 5. Those are the numbers under that line that are true in the inequality.
How are you doing back there?
Good, thanks for asking. Now I'm going to show you some of the special case problems. The absolute value of p is less than or equal to negative 7. What absolute values are less than or equal to negative 7?
None.
None of them. All absolute values are positive, remember? So there are none of them that are smaller than negative 7. So this problem reeks of seafood. Okay? No solution. You cannot put a number in there for p, take the absolute value of it, and get an answer smaller than negative 7. On the flip side, the absolute value of m is greater than or equal to negative 5. What absolute values are greater than negative 5? All of them, because they're all positive. You can't find a number that you could put in for m and get a number that will not work. All right, so now let's move on to one that's going to take some work. The absolute value of 2x plus 2 is greater than or equal to 4. Sophia,
Yes.
here I come again. Is this an and or an or problem?
And.
Is that just a wild guess? I'm on ride. There's got to be a better way to figure out if it's and or. Kruger?
It's or
Why?
because
Because it's
it's greater than.
greater than. That's right. It's greater than, so it's or. If it was less than, it would have been and. You with me? All right. So we're going to have a pigtail graph. Now it's going to break up into 2x plus 2 is greater than or equal to 4. 2x plus 2 is less than or equal to negative 4. Okay, notice how we flipped our inequality signs and we flipped our numbers. Well, we didn't really flip our numbers, but we inverted our number. And now our job is to solve each of those like we did last Friday. For x, subtract 2, divide by 2. and I get x is greater than or equal to 1. Subtract 2, divide by 2. I get x is less than or equal to negative 3. If I graph those, I should, if I'm doing my job correctly, get a pigtail-looking graph. Greater than or equal to 1, less than or equal to negative 3. Hairball, does that make sense? Okay. I'm going to let you guys try one on your own here, and we're going to see how you do. And if you do well, we're going to get you some problems to try for the quiz tomorrow. Here you go.